Okay, so welcome everyone. This is our fourth week, and in today's recitation, we'll cover proofs. Um, I hope you all recovered from last week's storm. It was kind of crazy. It was, in retrospect, pretty bad timing for our quiz one. But we kind of survived, and I'll talk more about that. I actually still don't have internet at home. Yeah, maybe at some point I'll share some photos of all the trees that fell around our house. And we've been really fortunate and kind of really lucky, the whole neighborhood. A bunch of big trees fell, but none of them hit any houses. So the way they fell is just almost a miracle, like kind of in between houses or towards the street. None of them hit any houses. But we still don't have internet, so hopefully that will get fixed soon. Okay, so let me talk a little bit about quiz one first. So yeah, I already mentioned, so we had major problems because of the storm, which caused, as you know, power outages and internet outages all over the place. And Bay and I really tried to put a few things in place, a few accommodations to help you, actually solve the quiz and so on. So there was a remake on Thursday, and we extended the deadlines and things like that. And I think all of you who wanted actually got a chance to do the quiz. One other thing that I wanted to mention, and I'll talk more about this in a second. Given these power outages and the storm and everything, we were really lenient in terms of allowing all sorts of different ways of submitting through emails and messages and so on. And we were accepting all sorts of submission issues and things like that. And that's going to change for quiz 2. We made a few announcements about that, so keep an eye on announcements on Canvas about this. But I want to talk about it as well, since I think it's really important. So, despite of all these outages and so on, during quiz 1, we certainly felt that there is still many students who have not read the syllabus and instructions for quizzes and so on. Because some of the issues that people ran into were not really related to power outages. It was more about not knowing where the quiz is, not knowing how to submit it, and so on. But the way quiz 1 went down, we were really lenient, and that is going to change for quiz 2. So for quiz 2, basically, if for whatever reason you fail to submit your solution using Gradescope and on time, so I'm not talking about email solutions, things like that. You have to do it using Gradescope. You have to take your questions and so on. You will get 0 points on quiz 2. So that's how we'll do it from now on. Because of handling dozens and dozens of exceptions and different kinds of submissions, really took a lot of time, and I think it's not the right way to go. So if you run into any kind of outages, like internet power and so on, you will have to support this by written letter from your power or internet company. And we will not make any exceptions in this regard. Now, we increase, for all the exams from now on, the grace period from 15 minutes to half an hour. So, after your 1 hour of quiz time is done, you have half an hour to submit your solution. And that is really a lot of time to submit it. You can have numerous attempts to do it. If your internet is not reliable at home, you can have a backup place ready that you can walk to or that you can drive to. Like a lot can be done in half an hour. And again, because of this, any kind of excuses like, oh, I didn't know how to do it on Gradescope, oh, my phone connection dropped and I couldn't do it, and so on, we are not going to accept those. I also strongly suggest that you read the syllabus and all the Canvas announcements and so on ahead of time. We were getting lots of very basic questions about submissions throughout quiz 1. We want to avoid that for quiz 2. And then, of course, really make sure that you know how to use Gradescope to submit your quizzes. That you know how to scan in your quizzes as the PDF document. We will not be accepting images, and that you know how to submit it. And you can do that ahead of time to make sure everything is working on your end. If you're struggling, you don't know how to do it, you have technical problems, come to office hours, and we'll try to resolve this with you. There's still 2 weeks before quiz 2, which is plenty of time to resolve any kind of technical issues you might have. But you have to work on it, right? You cannot just wait until you start doing the quiz and then realize that something is not working. Okay, let me make a couple more announcements and then I'll pause and take any questions you might have. Okay, so homework 1 scores are out. So you can find those on Canvas. Homework 2 is due soon. So it's due this Friday, September 18th and at 11:59 p.m. So don't forget to work on homework 2. There is still a number of office hours between now and the submission deadline. So if you're stuck on any of the problems, come to office hours, please. Quiz 2 will be in 2 weeks. So you still have plenty of time to study, but I wanted to give you a heads up. This quiz is going to be on proofs. And, in the past, students or most students typically find this quiz to be the hardest one. There'll definitely be all sorts of different problems with all sorts of different proof techniques in there. And students just struggle with it. And so, make sure to practice proofs a lot. It does take a lot of practice to learn how to do them. I mean, there are some common patterns and so on that can be learned only through practice. I hope you also noticed from quiz 1, typically we don't, the kind of questions that we put in quizzes are typically pretty closely related to the kinds of problems we solve during recitation, discussions, lectures, and so on. They're not going to be usually completely different types of problems. So if you solve lots of problems on your own, that really improves your chances of doing well on exams. So given the quiz 2 is coming up, and soon we'll also release grades for quiz 1, hopefully by the end of this week. I also want to talk briefly about how to get help. So if at this point you're kind of feeling you're struggling and falling behind, there are a number of avenues that you can pursue to get help. So first of all, there is Piazza. It's been quite active. You can always ask the questions there. We monitor it regularly. Then please come to office hours. There are a number of different office hour slots available throughout the week. It's really easy to join any of these, and TAs and me and Dave will try to help you with any kind of questions you might have. We also made an announcement about the tutoring center that our department has, which includes tutoring for 2100. So if you want to get help outside of office hours or from a person other than one of our TAs, you can also come to the tutoring center and work with one of the tutors there. And finally, if you haven't already done that, for some of you who like working like that, I think it's a good idea to bootstrap a virtual study group and work and talk to other students about the kind of problems you run into and so on. And here I would stress out that you should be mindful of our cheating policy. So you should not be copying from other students. You should not be solving problems together and so on. So it's fine to discuss solutions, but you should not have the same solution, exact same solutions in the end. That's what we consider cheating. And another thing that I want to mention and give you a heads up. So during my last recitation, we used Zoom breakout rooms to discuss solutions and so on. And I'll try to do more of that during today's lecture as well. Okay, so these are the announcements I had. Are there any questions about any of these? And I think our TA Ilkin is monitoring the chat and raised hands and so on. Okay. Great. Okay, let's then try to do our warm-up proof. Let me do the first one for you guys, step by step, and then the second one I'll give you some time to try on your own. They're kind of related, and so following the first one should help you to solve the second one. Okay, so what is the proposition? It says if 9 divides 10 to the power of n minus 1 minus 1, then 9 also divides 10 to the power of n minus 1. So this symbol here, you read it as divides. Okay. So what do we know? So we know we're going to prove this using direct proof because no other hints are given. And we know that 9 divides this expression. So that means that 10 to the power of n minus 1 is equal to 9 times some k, where k is an element of z. So this is the basic fact that we can write from our assumption. And from there, we want to prove that 9 divides 10 to the power of n minus 1. So basically, from this, we want to derive that 10 to the power of n minus 1 is equal to 9 times some L, where this L is an integer. So I wrote this down kind of as a side note because it's good to keep this goal in mind, because it gives us a hint, right? We have to somehow derive this expression from the assumption that we made. So let's see how we would get there. So from this, we know that 10, let me write it again actually, minus 1 is equal to 9 times k. Okay, so let's multiply both sides of this equation with 10. So we can do that because integers are closed under multiplication. So closure of multiplication. And that doesn't change the equation because we are multiplying both sides. So we get 10 times 10 to the power of n minus 1 is equal to, let's say 9 times k times 10. Okay, so when we multiply this out on the left-hand side, we get 10 to the power of n minus 10 is equal to 9 times k times, oh, sorry. Sometimes my pen makes this mistake, I don't know why. Okay, 9 times k times 10. Great. So, keep an eye on our goal. We're kind of getting there, right? We have 10 to the power of n. We have to get -1. So we get 10 to the power of n -1 minus 9 is equal to 9 times k times 10. And I'm really doing it kind of slowly, step by step here, so you can see the details. So from here, we get 10 to the power of n minus 1 is equal to 9 times k times 10 plus 9. And from here, we get that is equal to 9 times k times 10 plus 1. And that is equal to 9 times L, where L is an element of Z. And we can do this step because of closure of plus and multiplication. Okay, so we got that 10 to the power of n minus 1 is equal to 9 times L, where L is some integer. And that means that 9 divides 10 to the power of n minus 1. And that concludes our proof. Okay, any questions about this proof? Okay, so let me go through questions. So there's a question about, I got those formulas based on the structure of the division theorem. Is that correct? So that's a question by Erickson. Yes, that is correct. So that this 10 to the power of n minus 1 is equal to 9 times k. That follows from the division theorem. Another question, could you also use induction to prove this rather than direct? Let me think about this. So yeah, the short answer is yes, you could use an induction. You are trying to prove this though for all n. So that's, actually I take this back. Given that we are trying to prove this for all n, not just, let's say, n greater than or equal to 0 or n greater than 0, you would not be able to use induction because there is no really base case to start from. So induction, propositions where you use the induction, the kind of induction that we used always have the structure, prove this proposition, prove that this proposition holds for all n greater than 0. And then you know what your base case is and so on. Here, we are proving this for any n, and so induction won't quite work. This is a good question from Justin. Another question from Ellison. Why did you multiply both sides by 10 at the beginning? Yeah, so that's maybe let's say the hardest part of this proof that kind of requires some intuition. And that's why I keep saying, like, you really have to practice these proofs to gain this intuition. But let me try to talk about it a little bit. And that's why I try to do it step by step. And that's why I wrote this, I kind of wrote this goal for myself as a hint here in the top right? So this is what you want to prove. And this is what I was starting with, right? And so, when I look at where I'm starting and when I see where I have to get to, the hardest thing to match are the exponents, right? So I saw that I'm starting with 10 to the power of n minus 1, while in the goal, in the expression I want to prove, I have 10 to the power of n. So in my head, I was like, okay, how do I get from 10 to the power of n minus 1 to 10 to the power of n? Well, I have to multiply the starting one with 10. But I cannot multiply just that part with 10, because then the equality doesn't hold anymore. For the equality to hold, I have to multiply both sides with 10. And that's what I did. So that was the thought process. And I was really, like I said, when I was doing this, I really tried to stress out, write down your goal, where you're trying to get to, and look at your starting point. And you want to get from the starting point to the goal. And usually the hardest things to kind of match are exponents. Not always, but usually, right? And so that's where this multiplication by 10 is coming from. Great. Any other questions? Let me look at the chat. Okay. So I'll give you a couple of minutes to try this one on your own. So it also uses division theorem, but I would say it's simpler than the previous one. So it says if A divides B and A divides C, then A squared divides B times C. Okay. So let's see how we will do this. So let's first state our assumptions, the facts that we are starting with. So we know that A divides B. So that means that B is equal to A times some K, where K is an element of Z. And then we also know that A divides C. So that means that C is equal to A times some L, where L is an element of Z. Know that we have to use different symbols K and L here. If I used K again and wrote C is equal to A times K, my proof would be wrong. And that is because B and C are not necessarily the same number. So be careful about that. Okay, and want to show that A squared divides B times C. So what is B times C? B times C is equal to A times K times A times L. And that is equal to A squared times K times L. Okay, so we are almost there. So that's equal to now we do our substitution because multiplication is closed in integers. So you can write multiplication closed in Z. And then we get A squared times M, some M, where M is an element of Z. So B times C is equal to that, right? So from the division theorem, it follows that A squared divides B times C. And this finishes our proof. So this was a slightly easier one. Any questions about this one? Okay. Let's move on. Okay, so let's do one. I would say simple proof by contradiction. So we talked about that in the previous lectures. And okay, so we want to prove using contradiction. Let me just keep an eye on the chat. So there is a question on the quiz. We will have to write it in sentences, correct? I don't quite understand the question. You have to write, once you're substituting variables and introducing a new integer variable, you have to write, we can do this because of, integers are closed under multiplication and addition. You don't have to write actually a full sentence like that. It's enough to just simply note like ints closed under whatever star comma plus. That is good enough. So you do have to note it down, but it doesn't have to be a full-blown sentence. Okay, proof by contradiction, and I want to prove that if A is a rational number and B is an irrational number, then A plus B is rational. Okay, so when we're doing proof by and you assume P and not Q. So that's basically you're assuming that there is a counterexample to our statement, and then from this assumption we want to derive a contradiction. And if we manage to do that, we know that a counterexample cannot exist, and hence our proof holds. So this is what we have to assume. So it helps to understand what is P and what is Q in our proposition. So in this case, P is this whole thing. A is a rational number and B is an irrational number. So that's P. And Q is A plus B is irrational. Let me quickly look at the questions. Oh, I cut out a little bit. I hope it's working now. Okay, so let's write down P and not Q. So it's going to be P is A is rational. B is irrational. Let me write it like this. And then we have to assume not Q. So Q is A plus B is irrational. And so not Q is A plus B is rational. Okay, so this is P and not Q. And now from this, we have to try to derive a contradiction. Know that we don't really know how to deal with irrational numbers. We don't really know how to write them down, how to specify them, and so on. But we do know how to specify rationals. So we know that A is rational. So we know that A is equal to, let's say, X over Y, where X and Y are integers. We also know that A plus B is rational. So we know that A plus B is equal to, let's say, M over N, where M, N are integers. Okay, and so again, this requires some intuition. Where are we going to get a contradiction? Well, we don't really know how to express that B is irrational, but maybe if we kind of play with these two facts, we can potentially show that B is a rational number, which would then contradict this statement that we started with, that B is irrational. So let's try to see if we can get there. So A plus B is equal to M over N. That means that B is equal to M over N minus A. Great. Now we can plug in the assumption for A. So that is equal to M over N minus X over Y. Okay. We're still not quite there, but we are getting there. So that is equal to N times Y. That's what we have it below. And above we have to be careful, M times Y minus sorry about this. M times Y minus X times N. Great. And now we can write that B is equal to, we need two more symbols. I'm kind of, let's say K over L. So this whole thing here, we can replace with K. And this thing below, we can replace with L. And we can do this because integers are closed under subtraction and multiplication. So let me erase this. So I really have to get a better pen. Under subtraction and multiplication. Okay. So we managed to get to a point where B is K over L, and that means that B is rational. That follows from the definition of rational numbers. And this contradicts what we have above in our assumption that B is irrational. So B is irrational and B is rational contradict each other. And so we reach the contradiction, and that means that the original proposition holds. Okay, so let me look at the questions. Can we multiply A by n over n? I don't quite understand the question. I'm sorry. I'm sorry, Derek. Maybe you can ask it offline. By offline, I mean online during office hours. Usually that would be after the lecture, but there is no after lecture. Okay, so this was a simple proof by contradiction. So let's now do. We have 10 minutes left. I want to do at least one proof by induction. So let's actually do this one. So this one was actually in your lectures, but I would like that you give it a try on your own, and I'll split you guys up in breakout rooms, and you can discuss the structure of the proof with your peers. So you remember, for induction, what do you need? You have to figure out what the proposition is that you're proving. So what your P is. So in this case, it's simply spelled out for you. So we're going to prove this thing on the right. Then you need the base case. So you have to prove this for n is equal to 1. Then you have to write down your inductive hypothesis. I suggest that you assume that this holds for n, and then you have to prove that it holds for n plus 1 using the hypothesis. So so give that a try, please, and let me split you out into breakout rooms. So we'll rejoin in a couple of minutes. Okay. I hope this was interesting and fun. I hope you got to know some new people and so on, and got a chance to discuss this a little bit. So let's go through it. So first, we want to identify what our proposition is, what our predicate is. In this case, it's easy because it's basically given to us. So P of n is equivalent to this whole thing. Okay, and so the first thing we have to prove when doing proof by induction is our base case. And this depends on where n starts from. So be a little bit careful about that. You know, we'll see induction problems where it starts with 1, something starts with 0, and so on. So in this case, n is greater than or equal to 1. So we have to prove that P of 1 holds, which means that sigma I is equal from 1 to 1 of 1 over I times I plus 1 is equal to n is 1, right? 1 over 1 plus 1. So this thing on the left is equal to 1 over 1 times 1 plus 1 should be equal to 1 over 2. And we have 1 over 2 is equal to 1 over 2. So this proves our base case. Now we want to write down our inductive hypothesis. In my lectures, I mentioned, you know, you can start with n minus 1 and prove as a n0 hypothesis, and then in inductive step you prove that it holds for n, or you start with n and you prove for n plus 1. Both of these are fine. Somehow I usually find starting with n and proving for n plus 1 to be a little bit easier and more natural, but maybe that's just a personal preference. In terms of correctness, they're both fine. So what is our hypothesis? Inductive hypothesis. That's that P of n holds, which means that sigma I is equal from 1 to n of 1 over I times I plus 1 is equal to n over n plus 1. Okay, and then now we want to show inductive step. I'll run out of space here. So let me just forget about this. I'll continue here. So now we have our inductive step. Where we want to show that P of n plus 1 holds. So we want to show that sigma of I is equal to from 1 to n plus 1, 1 over I times I plus 1 is equal to n plus 1. Let me look this up a little bit. Over n plus 1 plus 1. Okay, and in the lecture, we've seen this proves with sums, right? You can express this sum from 1 to n plus 1 as the sum from 1 to n, which we have in our hypothesis, plus the leftover. So that's what we'll do. So on the left-hand side, we have sigma I is equal from 1 to n, 1 over I times I plus 1 plus the nth plus first member of this sum, which is going to be 1. So that's when I is equal to n plus 1. 1 over n plus 1 times n plus 1 plus 1. Okay, that is equal to. Now we can plug in our inductive hypothesis instead of this. So that's equal to n over n plus 1 plus 1 over n plus 1 times n plus 2. Okay, now we have to do a little bit of algebra. Remember, we have to show that that is equivalent to this expression here, right? So we have n plus 1 that multiplies n plus 2 below, and above we have n times n plus 2 plus 1. And when you multiply this out, you play with it a little bit, I'm going to kind of skip a step in interest of time. You get n plus 1 squared divided by n plus 1 times n plus 2. And these things cancel. And what you get is n plus 1 over n plus 1 plus 1. So we showed our inductive step. So we started with starting with this expression, this sum on the left, and using inductive hypothesis, which we plugged in here. We showed that we get to this, and that is equal to what we wanted to prove. And so this completes our proof by induction. So I'm going to stop here. Know that, you know, in your proofs, you don't have to like circle all these things and so on. I mean, that I'm doing this to kind of show the structure. Any quick questions before we finish? Okay, there's a quick question by Erickson. It's a good one. Should we have P of n be a different variable since the equality given is using n as a variable already? Short answer is no. I mean, you can reuse the variable from the proposition. But if you want to use a different letter, that's fine as well. Any other questions about this proof by induction? Okay. Okay, thank you all. And see you next Tuesday. Bye, everyone.
Thank you. Bye-bye.